original KP, right? So then when we flip it, we do 1 over that KP. And if we multiply it by the factor of 2, that's 1 over KP squared.
I missed why you multiplied by 2 in the beginning.
Oh no, this is what they gave us.
This is given.
Yeah, it's given. They said, what would the KP be of this equation?
But why did you multiply by 2?
Yeah, so this is the equation they gave them, right?
Yeah.
This is the original.
Original.
So compared to the original, they
you
multiplied by
figured
2.
Yeah, so they said, that in this particular problem, they actually had some where like it was just flipped,
Okay.
and some where it was halved.
Right.
In this particular case, it was doubled and flipped. So you have to know that it would step 1 over that, and then is it squared. That makes sense, right?
If it was halved, you would just be raised
Yeah.
to the half word.
So if we did
Do you
that,
have to plug back into to that one?
Yeah, so you have to plug in your original to find our new key.
yeah, so we just plug that KP in here. Yeah, yeah, that's a good question. So what if this was 1/2, that one was 1/2, and that one was a 1, right?
Right.
So what do? So everything got halved, right? So we raise it to the factor by which it was multiplied by. So we do that, we do raise it to the 1/2 power, which is the same thing as doing what? 1 over the square root of KPI. So don't lose your algebra skills, yeah. If we divide it by 5, we would do the 5th root of it, right? Yeah. That's it. That's easy stuff. You should be able to be pretty comfy with that, I think.
You can just do you could just take 2.26 times that, raised to 1/2 and still have the same answer? I mean, 1 over.
Yeah, so if you raise it to the 1/2 power, it's the same thing as square rooting out KP.
Yeah, yeah, absolutely, yeah. Yeah,
They
I know
mean the
it
same
works.
things used to.
Yeah, those are just equivalent statements right there. Yeah. Cool. So yeah, feel good with flipping, halving, multiplying by some constant, and knowing what's going to happen to the k. Yeah. What else is there? We went over the states, right?
Yeah.
So what's next? Just KP, huh? That's it?
KP and then let's just layers.
Yeah. So we don't really want to go too much in the lecture because practicing problems is really going to help this time, I think. It's more like not like lecture, yeah. So yeah, it's a lot of stuff we're going to go over. So. Do you want to do KP? Or do you want me? Whatever you feel.
You got KP now.
You chip in?
Yeah.
Sounds good. Cool. So, kind of like the last question, right? Pull it out to that. No, we didn't go over Q, did we?
No, it's fine.
Q, yeah.
Let's go KP first and
Yeah, so KP. So we'll talk about KP, right? So we said that we care about 2 states of matter, right? We only care if it's aqueous, and we only care if it's a gas. If it's a solid, it doesn't contribute to our K expression, right? And if it's a pure liquid, like water, we don't care about it either. So we have a really particular K expression if we're talking about gases, right? We don't use our concentration. We don't use molarities. So our K, our KP, is equal to the partial pressure of our products. That little p stands for partial pressure of our products over our partial pressure of our reactants. So this is kind of, it opens up things because it could potentially mean that you're gonna have to remember a lot of your gas laws potentially. He might not be that mean. Hopefully he's not. Yeah.
We got one.
Yeah, you got one of those, right? Yeah, yeah. I think I did too, actually. Yeah. So just remember your gas laws. What I will note is that it's all fair game, right? You guys had 101, so you guys know how to do this now. Remember your simple ones like PV equals nRT. Remember that equation, and then that's pretty much it. Maybe your combined gas law. You know, P1.
Is there something about the moles? You really only could be using moles.
Yeah. Yeah, that might happen if you're changing the conditions of your container or something like that, right? Yeah, don't forget your normal ones. And then, yeah, of course,
Yes.
Dalton's law, P total is equal to P1 plus P2 plus Pn, whatever you need. Yeah? So the sum of the partial pressures in a container will equal the total pressure. That's Dalton's law. So knowing these 3 equations will help you solve for P. That's all we care about is the partial pressures, right? Mole fraction, no, we don't want to worry about it, yeah.
Yeah. No,
Mole
not for
fraction,
the
I
6
wouldn't worry. Yeah. I mean, if you want, it's what? So P2. I think it's P partial.
P partial.
P partial is equal to XA times P total. That's fair game, I guess, too. Hopefully he's not mean, he doesn't do that to you guys, right? So that would be, remember your mole fraction is the partial mole. Or total mole, right? So we kind of have like a couple of things to keep track of, right? And it's all fair game. Most importantly, though, you should be familiar with this. That's going to be your bread and butter.
And that R is the 0.0821.
Yes, that's a good point. Yeah, that's.
When is it the 8.314? That's for.
That's
Those are
it.
your kilograms per mole.
Yeah, that's, and the units are liter ATM over mole K. That's important, yeah, because when you guys are solving for Kc and Kp, right, you need to use this constant R. So keep track of that. Whenever you're talking about R, your R in gases, it's always going to be 0.0821 liter ATM. Yeah.
8.314 was kilojoules?
Yeah, that's with energy usually. Yeah,
That's
like
usually used for Arrhenius.
yeah, Arrhenius equation. Yeah, yeah. When you guys were solving for like the activation energy, it was that divided by the R, which was the 8.314. Yeah, joules over mole K. So yeah, when we're talking about Kp, it's kind of hard to give you like a little lecture on it because it's all fair game, right? Partial pressures, that's all we care about, right? The products over partial pressures of the reactants. We say, yeah, no solids. No solids, no liquids. Cool. Yeah, this isn't going to be the full thing. We're going to go over some practice problems for you guys. But yeah, everything up to this point makes sense, right? Basically, everything's fair game.
When we say aqueous, it needs to, you're referencing to actually being ion.
Yeah, it means in water, and typically it means it's going to be ions. Yeah. But in this particular, in this case, yeah, you wouldn't. If you're using a Kp, you still wouldn't use aqueous, because that's clear, right? You're only using gases in a Kp expression. Only ever using partial pressures. That's all we care about. Yeah. Cool. Decent turnout. People start coming in. Thanks for joining us. Okay. Q. Do you want to do Q? Q.
Alright, so another constant we have is Q. So Q is we solve it the same way as K, so it's products to their coefficients and then reactants. The same expression, right? Products over reactants. The only difference is that this is not at equilibrium. Okay, so our K is at equilibrium. Q is not at equilibrium. Alright, so we can use Q to, so in a reaction, there's a couple rules. So you might be given K and they might ask you to calculate Q. Right, and then you have to compare the two, and that sort of tells you where your reaction's at in relation to it being at equilibrium. So it might be either have surpassed the point of equilibrium, or it might not have reached it, or it might be at the point of equilibrium. And so, should I go into the
Chateliers.
like where it shifts to the left?
If you want, yeah. I mean, you should know that what Q means. Yeah. If Q is greater than K.
Yeah, should I go into that? Or?
Yeah, for sure. Yeah, yeah.
Okay.
So what do you guys? What's up? Yeah, yeah. So you guys, while he's writing that, what's your understanding of what Q is?
Reaction quotient.
Reaction quotient, right? Because you're going to be using it a lot, right? So what he said was the main part is that it's not at equilibrium, right? So it's a snapshot of the reaction at any point,
right.
at any point, right? Meaning you mix some two things together, the likelihood that it's at equilibrium when you look at it is very unlikely, right? Unless you let it go on for a long time. So what Q does, it tells you where in relation you are to your equilibrium, right?
Right, so either so your Q might actually be greater than your K, so in other words, it surpasses the point of equilibrium. So in order to reach equilibrium, the reaction has to shift to the left. You have to favor the reactants to reach your equilibrium point. Or vice versa, if your Q is less than your K, your equilibrium shifts to your right. So it's going to favor products to reach equilibrium.
This is only happening with weak acids.
You mean equilibrium? No, not necessarily. No, it could be any reaction, yeah. So yeah.
That's next chapter.
That's next chapter. But you're right. Most acids are going to be like
Yeah.
equilibrium. Yeah.
Mhm.
Yeah. It could be any kind of reaction. Yeah. But yeah. That makes sense though, right? So then, what does this mean? Your Q would be less than your K. So which way do you have to go? You have to go back. You have to go this way to accommodate.
Right, you
for
have
it,
to shift this way in order to reach K.
This is going to really help, right? So in relation to, so if your Q is less than K, which way do you have to go to get to K? To the right, yeah? If your Q is greater than your K, how do you get back? Go to the left. Yeah, so then that's a way to do it and get the answer right.
Yeah.
But what you should really remember is that Q is what? It's products over reactants, right? Yeah, so then, yeah. So that means then, if this number is bigger than K, that means you have more products than you should, because your Q is bigger than your K. So how do you fix that? You go to the left, yeah. If your Q is smaller, that means you have more reactants than you should have. So how do you fix that? You go to the right, yeah. Just think about it, I mean, this is a way to get it right every time. But in order to actually understand what's going on, think about it in terms of what Q represents. Q represents the ratio of them over each other, right? Not at equilibrium. Yeah.
You said this is not just for gases?
Q?
Yeah.
So you know, Q is going to be like your best friend. Yeah, Q is for anything. Yeah, you can do Q at any moment. Yeah. Yeah. So experimentally, Q would be really helpful, right?
Yeah.
You would just get some of those little like vials and test the concentration at any point, right? And you'd be able to figure out which way it's going to be going, left or right. Yeah. So what's up?
A question like this would give us the order that the concentrations are
Do we care about orders?
at this point?
We don't, right? No. Orders don't. We
Yeah.
don't care about orders, right? Because what we're talking about equilibrium.
What is
So-
the M and the M?
Those are the coefficients.
Oh, yeah.
Right, remember that, yeah. So yeah, coefficients, yeah, we do not care about orders, right? So that's gonna be the hard part about this, is separating yourself from your rate laws and your equilibrium, right? But like dot your I's and cross your T's, right?
Gotcha.
Make sure you take a step, like a moment, to determine what part of the chapter you're doing while you're taking the exam, right? If you see Q is only found in the equilibrium chapter.
Right.
So then you're not using rate laws, throw it all away. You don't need it at that moment. But then remember it again if you get, you start hearing about, rates, and you start thinking, well, yeah.
Is QKC, that's always equilibrium, right?
Q is
No,
Q is never at equilibrium.
No,
Yeah.
I mean like in the equilibrium chapter.
Yes.
Oh,
Oh,
yeah.
in the
KC
chapter of
as well.
equilibrium, if you hear the word Q, yeah, you're in that chapter.
Or KC?
KC, yeah, K sub C means you're in equilibrium.
Okay.
Also KP would tell you you're at equilibrium.
Okay.
And you can like flip over your sheet to your KP section of your cheat sheet, right? Yeah, you flip it over when you see rates and flip it over when you see Qs, yeah.
Gotcha.
Yeah. Does this make sense? So if your Q is greater than your K, which way does it go?
If it's greater than that,
It goes left,
Yeah.
yeah? To accommodate for that. If your Q is less, it goes to the right, yeah. That's gonna make your life easy for sure. Okay, what else is there? Le Chatelier, that's it? Yeah. Le Chatelier. Le Chatelier's principle. The principle of Le Chatelier.
You you guys did the elementary equations? Or?
Yeah, we kind of.
That would be in what chapter?
14?
14, yeah, yeah. 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 Okay. Oh yeah, yeah. Which one was that one again? It was. Oh, that one's good. 11. Yeah. Okay, we'll do that one for sure. That's such a good question. Really good. Le Chatelier. I'm not going to attempt to spell Le Chatelier's principle. I'm going to put LP. Yeah. Le LCP. Least common principle. LCP. Le Chatelier with a little comma. I'm not going to try to spell that. But all it means is that, let's say you have something. It's a good reaction. Equilibrium. Let's see if we can find one. I'm going to give you a real one. That's easy. It's just small. They're gases too. Yeah. H2, right? So we have H2. What is it? H2 gas. So notice they're all gases, yeah? So then we can start talking about equilibriums and so on, right? So we're talking about, if this was at a solid, would we care about it in our equilibrium? No, right? If this was a liquid, no. Because they're gases, we care about them. Okay, so what Le Chatelier's principle tells us is that if we, let's say this is at equilibrium, at EQ, currently, and we apply some stress to this reaction, it's going to shift to accommodate that stress, right? So if I increase this guy right here, well, what would that mean? Would that mean what would my Q be at that moment?
It's going to be greater than
It would be greater, right? My Q would be favored because my Q would be larger than my K, right? So which way do I go for that? And the left, yeah. Okay. So yeah, if you increase the concentration of one side, it shifts to the side, the other direction, to accommodate for that. You have too much, you got to push it to the other side. It's like a seesaw, right? If the weight gets heavier here, you have to push it to the other side to accommodate the weight. That's what that means, yeah? And that's for concentration. Current, only concentration right now, right? Because with pressure and everything else, we have different rules. We can't use the same rules. But we can think about it in terms of concentration, right? So if I increase the concentration of H2, which way does it go? To the right. If I decrease the concentration of H2, which way does it go? It means I've lost weight here, right? So the seesaw goes up. How do I fix it? I add it weight to go this way, so it goes that way.
Right, we can also
Yeah.
say that because the concentration here decreased, then we have to form more of the reactant so that this concentration can go up.
Yep.
So it shifts this way.
Yeah. So it's not just always gaining concentration, it's sometimes losing it, right? So if you lose a little bit of this, it goes this way to accommodate that stress.
To produce more of it, so that now it's back at equilibrium.
Yeah. Does that make sense? Yeah.
Can you talk about it in the endothermic and exothermic?
Yeah, we're gonna go through each one. Yeah, yeah. No, each one. Yeah. So this is a good example too, because this is also gases, right? Right. So if what do we care about? This is actually 2 and 2, so that's not really good. That's kind of a bad example. Let's get one better. Here, give me a gas one. Yes. Good, Dieter. Good, Dieter. Good, Dieter. So N2 and what?
N2O4.
Yes, Dieter. N2, what is it?
Oh, which one?
Put down Dieter, look at
What was that, 202?
Plus 2 O2 gas?
Yields 2 and O2.
Yes. This is good. This guy is at equilibrium, yeah? Okay. So let's say this is at equilibrium, right? Notice that they're all gases, yeah? So if I increase the pressure in this container, the side that it affects is the one with more moles of gas. So how many moles of gas do I have on this side?
3.
I'd have 3 moles, and here I'd have just 2. So if I increase the pressure, it's going to affect this side more, and to accommodate, it goes this way. To accommodate, is that okay? It's like we're thinking about it in the context of concentration almost, right? Meaning this has more moles, so think about it like adding concentration to this. So it shifts that way to accommodate it. So, is that good? Yeah?
Oh.
Yeah, and then if we were to, so then it's not as easy as me telling you that I increase the pressure, right? What if I lower the volume? What does that do to pressure? It increases pressure, right? Whose law is that? Do you know? Oil's law, right? So what is that? The volume and pressure are inversely proportional, right? So keep track of that, yeah? If I increase the volume, what happens to pressure? It goes down, right? Man, if I had a balloon and I increased it to the size of this room, you would expect the gases in the container to have not as much pressure, right? But if I, in the other way, if I squeeze this room into the size of a balloon, it would be really highly pressurized, right? They're inversely proportional, right? Right? So they'll do that too to you. They'll say the container was tripled in size, right? Which side does it go to? If it was tripled in size, what happens to the pressure? Pressure goes down, right? So which side does it affect more? This side, right? There's more moles. So in essence, we can say, since it's decreasing pressure, we can think of it as lowering concentration of this side. Which way does it go? That way, to accommodate it. Does that make sense? Yeah? So like, think about what side it affects more. If you increase pressure, it'll affect this side more and go this way. If we lower pressure, it affects this side more, and to accommodate it, we have to go that way towards it. Your notes have a really good explanation of that. That's like a little sentence that if you look at Fenton's notes, it's really good. It's really like, it explains it really nicely. It affects the sides with more moles in it, but it's even like, it's put more succinctly than that, yeah. It's really nice actually, yeah.
As soon as you actually look at the reactants and the products, the one that has the most moles, then that's your starting point in reference to what's
Yeah,
to be applied.
so if they're asking you which way does it shift, right? You should step back. You're in chapter 15 or 14, whatever you are. You're in the equilibrium chapter, right?
Yeah.
Take a step back, right? You're also talking about shifting. So we're talking about Le Chatelier's principle. Pull yourself back. Which side has more moles, right? Of gas, right? Then you say, okay, then I put 3 and I put a 2 here, right? Rather than just tackling it, right? And getting it wrong, take a moment. So take it back, take a step back and think about which side's being affected more by the change of the environment, right? So yeah, that's how you approach these problems and don't make dumb mistakes, right? Yeah.
If you have a solid, you don't count.
Yeah, we don't care about solids, right? So if we're talking about shifting, solids have no effect, right? Yeah. What's another way we can do this? What's up? Yeah, let's pull it up. We gotta do one for endothermic. Can we pull one for that? if we can? Endothermic. I don't want to write it all down. Thanks. We're pulling up a problem because it's a lot of writing. I don't want to write it up. So. There it is. And we're talking about this one. Can you guys all see this? Yeah? So which factor will not increase the concentration of ammonia? What's the formula for ammonia? NH3, right? So don't lose track of that too, right? don't get destroyed on problems that aren't hard, right? We're talking about this, right? Will not increase. Okay? So in this particular one, if we increase the concentration of N2, which way would it go?
To the right.
To the right. So what would that do? It would increase the concentration of N2. So that's not that one, right? We're talking about not increasing it. Increasing the pressure. Pull yourself back, right? Ask yourself, how many moles are on each side, right? How many on this side? 1, and there's a hidden 1 there, so there's 4. How many here? 2. So what happens if we increase the pressure, which side does it affect more? This side, right? And which way does it go? To the right. Which would it affect? Increase the concentration of NH3, which is what we're not trying to do, right? Does that make sense? Good. Increasing the concentration of H2, what would that do? Well, that would, increasing the concentration, that's a standard Le Chatelier principle. It would bring it over here, which is not what we want to do, right? We don't want to produce any of this. This brings up the last Le Chatelier's principle stimulus, which is if you have an endo versus exothermic reaction, right? Increasing temperature versus lowering it. What we care about is where would this be in the reaction? If you remember your 101 knowledge, right? If it's exothermic, we can think of it as being in the products. It'd be hanging out here, right? So if I rose the temperature, we can kind of think about it as increasing the concentration of it, this. So where does it go? To the left. To the left. So what would that do? That would be our answer. That would be answer D. So do you see how like each step along the way, like D was the right answer, but like that, you had to go through a bunch of different, like going through each scenario in your head. And how many of you would have gotten, you know, one of those wrong along the way, right? So take your time with it, right? Write the little moles above the thing so you don't lose that problem, right? Now, and then remember, exothermic reactions, we find it on the right side of the reaction. Endothermic would be found on the left. So if this guy was positive, 92, it would belong on the left side of the reaction. Does that make sense? Yeah. So then if we increase the temperature and it was endothermic, it would shift it this way. That
Right,
makes
so it's
sense.
endothermic, it would show up as a reactant, right? So if this was endothermic, right? Pretend that was endothermic, show up as a reactant.
Yeah, we would think about it as increasing the concentration on the left, and therefore it would push it to the right. Yeah. So remember, like, if it states endothermic, it may not give it to you explicitly like this, right? You might say it's endothermic. Just remember, endothermic, it's going to be found on the left, exo on the right. That's worth putting on your cheat sheet, I'd say. Yeah, it's worth putting on there, for sure, yeah. What's up?
Can you explain why it wouldn't be B? I mean, I'm sure it'd be obvious, but I mean, just so I have a
For
thorough
sure, yeah.
understanding.
So increasing the pressure, if we increase pressure, we care about gases, right? Right? Well, how many moles of gas do I have over here? 4. And over here I have 2, yeah? So which side does it affect more?
The NH3 ammonia?
No. The side with the more moles gets affected by a change in pressure. So it would affect this side more. Increasing pressure would push it that way, which would increase NH3, which is what we're not trying to do.
Okay.
Yeah. Cool.
So, this is what I put, pressure affects the side with more moles. So if it's decreasing, it goes to more, like,
Yeah.
the normal?
Yeah, so that the way your notes say it is the pressure decreasing, it shifts towards the side with more moles. The pressure is increasing, it shifts towards the side with less moles. So that's a good, your notes puts it perfectly, in like really less few words. Rather than like us trying to like explain it, it's like, it's really nice. Yeah, that's a good way to put it. Yeah. Cool? That's a good example. Let's do 9. You want to do it, Dieter? 11? Sure. Do it, Dieter. You got it.
Is it practice test?
This is your practice test.
Yeah, but multiple choice.
Yeah, so if you guys are new to Fenton's class, then you should probably be aware that these are available online, these practice tests, and they're really representative of what his exam will look like. So it's multiple choice. Yeah.
This one includes both, 14 and 15?
What's up?
That practice one includes both 14 and 15?
I think so. Yeah. Yeah. It seems to have both. Yeah.
All right, this one's a little bit different. So you still have an equilibrium, but now you have ions in your solution. So if you increase the concentration of OH, what is that going to do? Like, how is it going to shift, and how?
Increase in OH?
So that's obviously not going to increase the concentration of H2Cl4, right? right?
Yeah.
Alright, so A is not right. Increasing the mass of HGO. If we increase the mass of this, is this really, since it's a solid, is it really gonna affect the ion here, HgI4? No? If we add a catalyst, how does that affect equilibrium? Does it affect equilibrium at all if you add a catalyst?
Right, speeds up the reaction.
Yeah, both ways.
Yeah.
So then, if you add HNO3 to the solution, what is that gonna do?
So notice HNO3 is not found in this equation, right?
Right.
It's saying, what if I added some
But
randomly?
Can it react with something?
So it can react, right? You have an acid and you also have a base, right?
Right.
So what is it gonna react with?
With the OH,
Right. So if it reacts with the OH, what does that form?
water,
Right. You have water here, you increase the water here, right?
right,
How does that affect the equilibrium?
to the right.
Right.
This is a really good question, like really good. Like did you notice how really good this is?
That one's cool,
This
yeah.
is like reminding you that of acid-base neutralization reactions, like really good reaction. So this, you can look at this through multiple ways, right?
Yeah.
If it's reacting with this, that means you're losing this,
Right.
right? Who cares? Let's say you didn't even know that it made water. You do know that you're losing this, right?
Because it's reacting?
Because it's reacting, right? Yeah.
Because it has to, because that's an acid.
Yeah, let's,
Only
we can,
base, the
we
obvious
can almost
base.
like reword this, right? What if this wasn't an acid base, but let's say when we poured something in, it formed a precipitate with one of our products. That's another option, right?
Right.
If it forms a precipitate, then do precipitates have any effect on our overall equilibrium?
No.
They don't, no? But we can think about it as losing this.
Right.
So we would shift this way to do that, right? So you have, as you can see, we kind of gave you like very easy rules to understand, but they can really get difficult all of a sudden, right? They can kind of make it, they really test your knowledge. So yeah, don't be too frightened. This is probably the one that people would probably pick, right? They think catalyst makes it go, activation energy goes this way, right? Yeah. But if it's at equilibrium, right, a catalyst would make it go fast in both directions, right? So it wouldn't have, and it's already at equilibrium, right? So then, of anything, what did you learn from this? You learned that a catalyst will not affect effect.
That only affects the rate of the reaction,
Yeah, it would, right?
not.
Yeah, the rate of the reaction.
Right, because it's at equilibrium, so
The rates are equal.
Yeah, it would speed up both forward and reverse.
Yeah.
So nothing really happens.
Yeah, it would increase the rate, but what, at equilibrium, the rates are equal, right? Yeah, so you would push it in.
Can you explain that again? I'm really lost on why it's just D.
Okay. Do you wanna-
Go ahead. Yeah.
You wanna know why it's D? Okay, so HNO3 is an acid.
So,
right?
so for this, we don't care that we don't have any gases, right? I mean, it's solid, liquid, aqueous. So we don't care that we don't have any gases, we're not looking into that?
Yeah, that's not a big thing right now, right? So gases only matter if you're doing a pressure change, right? Yeah, which we're not doing.
So we have HNO3, which is an acid, right? And we have OH here,
Right,
which is a base.
okay,
So what happens when we put acid into this mix? It's gonna react with the base, right?
right.
So then our concentration, so if we were to make a little formula here for this very reaction, whatever that is, right? So the hydroxide will react with the nitric acid, right? Because this is a base and this is an acid, and it'll form water, right? But we're not going to worry about that right now. So it's going to react with this. So it's going to be used up in the reaction, which means that this concentration will decrease.
Okay.
Right, so this concentration will decrease, and the equilibrium will shift this way to the right to make up for this decrease, to produce more OH. Does that make sense?
Yeah.
It's pretty tricky.
What's another way
Once
to
the-
do that? Like, I guess just mixing up with like a base in the question versus an acid in there? Or?
Yeah, like they might have, like you might have an acid here, and then yeah, adding some base.
Yeah.
Once the hydroxide is gone, then the mercury iodide increases.
I'm sorry?
Because of the absence of the hydroxide, then the mercury iodide increases.
Well, yeah, because it doesn't, the reaction shifts,
Right.
like, not because, it just shifts because you're losing products, right? It like just
gotcha.
it all shifts. Yeah. So by definition, you'll have more of this.
Yeah.
Yeah,
Yeah.
both-
Even
yeah.
though it wasn't affected directly,
That's a good point.
it is shifted here
Yeah,
still.
so
It's
both,
more moles.
yeah, so both of these, it will shift this way to increase both of these.
Yeah.
Yeah.
So that's worth knowing, right? Sometimes you have one product, right? And you increase that product when it shifts this way, right? But when it shifts this way, it increases both. Right? That's really like, I guess that's like, that's not explicitly said.
Yeah, that's important.
That's really, yeah, that's good. Yeah. So that's a good question. Expect every multiple choice question to be like this. Expect every one of them to be like this. And I would honestly say, like, as a good test taking technique, look in this region. Right? C and D, right? Because you are going to be tempted to choose the first thing you see, right? And unless you're completely positive you're correct, you should look at your options.
Yeah, read it on the.
Read it, yeah, read it. Take another minute, right? Because he's gonna put answers here that are gonna trick you, that are meant to make you choose those.
Yeah,
So
he
read a little bit
knows what
into
you're
it.
gonna pick.
Yeah, that's why they put them there. That's why they put them there. So yeah, that's why they, yeah.
It's not gonna be that bad, right?
No, it's not horrible.
Yeah.
No.
This isn't your hardest exam. They're not like, you're not at Harvard, right? You gotta just take your time with it, right? Yeah.
Just read it and all.
You guys are in Fenton's class, and more than likely, you're gonna get more time to finish the exam anyway. Right? They'll push the exam into the lab.
Yeah.
Take your time. Take your time, yeah. This is good, number 8. Number 8. It seems like we're kind of just diving into the problems, huh? Just diving, we're just going to problems, yeah, forget, yeah, we're doing fine. Number 8's good. Yeah.
See better.
Can you see or no?
It's all.
It's a fuzzy, yeah?
Yeah, there we go.
Is that good? Yeah. So which of the following equilibriums would, sounds funny, plural equilibriums, would a change in volume have no effect? Right? So change in volume, right? So what do we care about with gases and changes and shifts?
Number of moles?
Number of moles, right? Yeah. Because why? Because if no side has more moles than the other, then it won't favor any side, right? So take your time and look at the different states, right? It can kind of mess with you if there was some solids juxtaposed in here too, right?
Right.
So calculate the number of moles in each, and if they're equal on both sides, changing volume will have no effect. Yeah.
So how many moles are for A?
4.
4. This one?
Two.
And what about this one?
Two.
We're gonna see right off the bat.
Yeah.
Which one our answer is gonna be.
Yeah. And then
Or maybe you want to check your.
then check it.
Sure.
Then check it, right?
Which one? How about this one? This one?
1 and 2. So yeah, you checked it, right? Like you might have like looked at it and you might not have seen that there was a solid hanging out there, right?
Right.
And that would have messed you up, right? Yeah. So take your time. Take your time. Yeah. This could have been harder with some solids as it was in there. Yeah.
Like they don't need same.
This is good. 7's great. So these are all the Chatelier problems, right? Determining where it would shift, right? So which of the would yield the most amount of oxygen, right?
Right.
So products. We have gases, so we should focus on the number of moles, right? So that'd be 2 here and 3 here. Cool.
Is this reaction endo or exothermic? So
Endo.
it means it's what?
On the left side.
Yeah.
Yeah, so be over here, right? So 114. Okay. So what would increasing temperature do? Which way would it go? It would go to the right, right? If you increase temperature,
Yeah.
it goes that way. So we have 1 going that way. That's good. High pressure. High pressure affects the side with most moles. Which side has the most moles?
To the left.
To the right side, right? Has most moles. So which way does it go?
To the left.
To the left. So we have 1 going backward now. Okay. So it cancels essentially, right? We don't know by what factor it was changed, but we do know that one's right and one's left. So we can kind of, we'll keep track of it, right? I imagine if we get 2 in the same direction, towards the right, that's gonna be our answer, right?
Okay.
High temp,
Right.
right. Low pressure.
Right.
Low pressure affects the side with more moles, which we can think of as lowering the concentration of this, so it shifts that way to the right. So we have two rights. Just double check, see if it's good practice, yeah. It's probably gonna be B, yeah. Low temp. We can think of it as lowering this,
Yep.
so it goes that way, to the left. High pressure
Right.
affects the side with more moles, which is this one, so it goes that way. Low temp would go to the left. Low pressure affects the side with more moles, goes to the right, yeah. So B is our answer, yeah. Yeah. So when you're doing these, like when you're taking these practice exams, the utility of it isn't just getting the answer right and moving on, right? But also practice this, right? When you're doing it at home, because you're gaining from it, right? The direction, right? If you just circle the right answer, you're like, okay, great, what did I learn? I know how to evaluate this one scenario, right? But you can change the question, right? Which side would produce the most amount of nitrogen dioxide? It would be C in that case, right? Cool.
So did you say, low pressure affects the side with less moles?
More moles, yeah.
More moles?
In what way? Like it would go towards that, yeah. It affects that side in such a way that it goes towards it.
It also affects the side of more moles, whether it's high or low
Oh,
pressure.
when it's high, it's the low, it goes to low.
Whether high or low pressure, it affects the side with more moles. In what way? If it's low pressure, you can think of it as lowering the concentration of that reactant or product. Yeah, if you look at your notes, there's a really, really good one. It says, the way the book says it is, low pressure, it shifts towards the side with more moles. That's what it says. High pressure shifts towards the side with less moles, yeah. Okay.
Just pulling it up.
Yep.
Oh, you have the online version? He's pulling it up for you, John. He's pulling it up for you.
We're almost there, dude. Cool.
There.
He might give you a picture problem as well, which is totally possible, yeah. How fast that is, yeah. Gives you guys picture problems, yeah.
Yeah, he puts like the simplest.
Go down a
picture.
little bit, yeah. I think it's down. No, it's up, I guess, yeah. Is there a summary of Le Chatelier's principle or no?
In the notes, is it a spread?
That's temperature, so
Oh, yeah, it's on.
go down,
The red.
down.
If you guys have the book, you guys
No,
should
we
look
don't
at
have it.
every picture that he puts in there, or that the book have. Because he may actually, we should put an answer like that, just picture.
Just a lab, like the
Not
complex.
simple, but yeah, it's
ionic
hard, if
equilibrium.
you can understand that picture.
If like they have trouble with the,
And that's just like
the temperature,
understanding
just think about the
basic,
lab and what they did.
To understand, like, not.
They put it in ice, and it went to like color.
Because it was endothermic versus exothermic reaction?
If you guys have trouble with the heat portion, like if you think about our lab with the complex ion equilibria, when we put it in ice, whenever you put it in the ice bath, it went to like that pink color, right? So that means that the equilibrium, it basically shifted more towards the reactants. And that's because in the equation we also had heat, so I'll just use delta for heat. But basically we took it away, so you can think about it going in this direction when you take away heat, so it shifts the reaction in the same way. Because you're removing heat, right? But then if you add heat, if you just add heat here, it's going to shift the equilibrium this way, right? Because you're putting a stress on the left side of the reaction. So it'll shift this way, and that's why we saw it even in the lab, whenever we heated it up, it turned that really like dark purple, remember?
Yeah, some like related to stuff that you guys have seen before. That's a good method. So the only thing we didn't cover was KC from KP, right? Or KP, basically.
Yeah.
Yeah, which was, we should get through that again. It's above here. Where are you? Oh, and ice tables, what we can do is.
Page 28.
Yeah, I'm looking at it, yeah, thank you.
The only thing we didn't go over, right, was this guy right here, right? Right, so this is, you don't necessarily need to memorize the equation, right? But you should know some subtleties to it, right? That this guy right here, the delta N, right? That represents what? The moles of what? Change in moles, right? From what? Products to reactants, right? Or whatever way you want to think about it, right? So it can be from right to left, right? So what that means, and I want to point this out because it won't be said explicitly, if it's the moles of products, right? Let's say that's equal to 0. What does our equation simplify to? It's Kp equals Kc. So what is any number raised to the 0 power? It's 1. So our Kp is equal to our Kc. That's never really stated explicitly. Yeah, grab one. Yeah. So that means then, yeah. So if the question asks, there's a question in our practice test that we can pull up, and it states at which of the following reactions will our Kp equal our Kc, right? And you can kind of look at it all day and be like, well, I don't know, but we can try find it. Is it?
Oh,
Cool. Yeah. It's a good question. Yeah, you should finish your review this weekend. Right, give yourself a whole week to like digest the material. Right? Well, actually, you don't even have a week. You have 2 days. Yeah. Yeah.
I'm like, what? Did
You should have had
exam?
them. Ideally, you should have had them done by today. Yeah.
Yeah, I'm doing
Yeah.
it today.
Yeah.
And then test for you tomorrow.
I gotta start studying.
Is it in this one?
Yeah, I found it.
Hurry up, Peter.
What is the equilibrium concentration? Oh, I see what you're saying. I see. Yeah, this is good. We'll get started. Revise on. Let's start doing calculations, right? So if you have this print,
Right into it.
yeah, we'll jump right into calculations. I guess Dieter just like he's like, do this one. Okay. All right. So we're gonna start doing ice tables and so on, right? But this one, I think we don't actually have to do that, right? In this, or maybe we can, right? So equilibrium concentration. So when we're doing ice tables, do we care about moles or do we care about molarity, right?
Molarity.
Molarity, right?
Yeah.
So that means that if they give us a starting mole amount, we have to convert that. But the nice part of this is that we're dividing by a 1 liter because molarity, moles per liter. If that number is 1, well, it's just moles is equal to molarity, right? That number was 1 in this case, dividing by 1. So each of these that you see are the corresponding molarities, which is nice. Yeah. What do they want? So equilibrium concentrations. That's just our mixture of the allow place in the living fast, allow to come to equilibrium. The equilibrium CO2 is that.
Yeah, so
Yeah.
this is our reaction, right? We know our concentrations initially. CO2 is 0.1. what's given to us, right? Yeah, okay. So they don't give us this concentration right here, right? So we just assume it's 0 because it's there's a reaction going on, right? And these reactants are reacting to form these products. So initially there is just no CO.
Would you care for the space of each?
What do you mean?
Like gas, liquid, gas.
We would, yeah, absolutely.
Yeah, these are all gases, so we're fine. We don't have to worry about this problem. Okay, so now we have to find the change for each one. So in order to determine our change, we have to look at our coefficients, right? What are our coefficients here? Just 1 to 1, right? They're all 1? Right, just 1. So they're all going to either decrease or increase by a factor of 1. Okay, so we have to calculate what this is. So if we do the calculation.
Anybody have a- What is that?
Yeah, what is this?
Can somebody do that? What does that change? Yeah. What is that? 0.006?
Yeah.
0.44, yeah.
What was that again?
0454.0. Wait.
That's not right.
Wait,
Nine
That's not right.
0.46.
That's not right at all.
90.9046.
0.9.
Oh, wait a minute.
That doesn't sound right either. No. Yeah.
0.0046.
Thank you. Yeah.
Yes.
Thank you.
Alright.
All right. Out of curiosity, because what did you guys do? And how did you get that wrong?
I put 1 instead of 0.1.
Okay. How did you get that wrong?
I subtracted the equilibrium from the.
So how do you do this? How do you get from here to here?
From
What do you do?
Initial to the end.
Subtract these two from each other, right? That's not, nobody tells you that, right? You subtract these two numbers and you get that, right? Okay.
FYI.
That's fine. Okay, cool. All right.
Everything good so far?
Is it negative?
Vapor? Vapor? Vapor, yeah.
I subtracted the rate, I wrote it wrong.
Okay. You want to get,
Yeah. All right. So remember from the previous, chapter, we said that we had this generic formula. Right. We had something like this, right?
Yeah.
And we said that our rate law was, we said our reactants were negative. Okay. And then our products are positive. The same thing here. So because these are reactants, they're depleting, right? So it's like with these negatives here. And we put our products are forming, so they're positive. Okay, so then to calculate the other ones, because they're all either decreasing or increasing by the same factor, this is also going to decrease by 0.046, and these are also going to increase by that number.
Does anybody know why? What's affecting the change? Like, why are they the same? The molar ratios, right? Yeah. So what would you do if there was a 2 here?
Divide by 2.
You would have to, your change for everything else, if it was 1s, would be divided by 2.
Right.
Does that make sense? We're gonna try to do one like that for sure, but yeah, sometimes it's not clear cut. But if you ever forget, you can always use your molar ratios that you're used to doing like you did in 101. Right? So you have 2 moles of this, there's 1 mole of that. Yeah.
Oh.
0.0454 for the equilibrium concentration.
H2. 004?
Wait, hold on, what?
004?
For this one?
0.004?
0.004?
I'll pull up the answer so you can.
Did I get it wrong again?
Yeah, it's 0.0454.
054. 0.054.
No.
0.054.
For H2, this is what?
No, 0.054.
0.054.
Yeah.
This one, okay.
Sorry. I'm gonna get those wrong in there.
Hopefully not.
They'll say.
Point like this?
Uh,
0.045.
We're all gonna fail together.
Okay, hold on.
And I'm looking at it. Hey, you wanna use it?
0.0454.
Alright, what about this one?
0046. 0.1046. 0.1046. Yeah. 0.1046. Yeah. Right.
Alright,
Subtracting 101.
so So these are concentrations.
Forget your subtraction and multiplication rules, guys.
Goodness.
You're doing good on time.
These are concentrations at equilibrium for each reactant product. And then that's what they're asking for.
Okay. So we're not, yeah, I guess that's equilibrium concentrations, huh?
All right.
Yeah. Cool. So part B, yeah, so does everybody realize that we're done?
Yeah.
Yeah, okay, yeah, why? Because this is the E for equilibrium, right? So, okay, so we're done with that part A. Okay?
Is it okay just to leave like that on the test? They'll know
Question.
that's-
If I were you, I would circle everything and write it clearly.
It's always gonna probably be two-part, like for all the questions that we've done, it's always like calculate KC with it, so.
Okay, so it says calculate KC, so our formula for KC is equal to our concentration of products or concentration of reactants, the respective powers. Then KP equals KC times RT delta, right?
Tell me. Yeah.
To calculate the KP. Okay. Open.
So which one are we going to calculate first?
KC?
Right, because we have our concentrations for at equilibrium, right?
Right.
Could you solve for KP yet or not?
Not yet.
Right, can't solve. Show me that. That's good. Yep, that's it. You're good. Oh, I want the answer, 0.11, sorry. Oh, 0.11.
I won't give it to you anymore.
Yeah. Nope, you're not allowed to give answers anymore. Cool, so what's your KP? And I want you guys to, like, without doing any calculations, what's your KP? Look at your equation.
What's your KP?
Yeah.
Yeah.
Yeah. What's your KP? KP is what? It's equal to KC, right? Why? Because your moles are the same on both sides, right? So you could have, that saves you about 5 minutes worth of work, right? Right?
It's minus in the middle.
No, I'm saying we have the same number of moles here. We have 1 and 1, that's 2.
Oh, okay,
2
okay.
equals 2, right?
Mhm.
Right? So keep track of that. Save
Sure.
yourself a whole lot of work and effort, right? If you're
Right.
calculating KP, you need to get delta N.
So this is,
So
this
look
is
at
0. Then we say this is also P.
Okay, so just to like clarify, when moles are the same, KP equals E.
Absolutely, yeah. KP is equal to KC when moles are equal on both
Right,
sides.
because-
Of gases.
Okay.
Of gases,
So we said,
yeah.
delta
yeah.
N is.
That's important.
Change in moles.
Right, number of moles for the sum of the moles of the products minus the reactants.
What's 25 plus 272?
298, or 298, yeah.
Yeah.
Okay, and then what the N is? So since the delta N is 0, right?
Oh, so your
Or what's anything raised to the
Zero.
0 power?
It's 1.
Just 1, right? So you're just doing KC equals 0.11 times 1, which is just 0.11, right? It's the same exact thing.
Yep.
On the chapter 14, your R is different. Your R will then be the 8.3.
Yeah, so what's the units? What's the units for R? For the R in chapter 4, whatever mechanics.
Kilojoules. I mean,
No, it's in, yeah, so it's joules over mole times Kelvin.
Right.
So, do we care about joules right now?
No.
No, right now. Yeah, joules are gonna be useful with energy and so on here, but not here.
Is it liter?
ATM. Liter ATM over mole.
Yeah,
Yeah.
liter ATM most of them.
Yeah, whereas if you're thinking about gases, right, it makes sense to use the gas constant, right?
Right.
0.08.
Yeah.
I'm sorry?
Units phase.
For this R, liters times ATM over mole Kelvin. Yeah.
So what is temperature in this equation? Like you just don't use it, it's just never show you off?
Well, we would absolutely use it. It's just that in this particular case, the N is 0. Delta N is 0.
Oh, okay.
So you're right though, yeah. If there was 3 and 2, we would use 298. Yeah.
Right.
Yeah, so remember also that that's a good question because the R will tell you the units that you should be using, right?
Right, so our R is 0.0821, right? Temperature's units of Kelvin, that's our constant, right? 8 liters ATM moles Kelvin, so our temperature has to be Kelvin.
Yeah. That make sense, yeah?
Yeah.
Cool. Cool, so yeah, looking at the units will help you a lot, yeah. This is kind of a math. Turn into kind of a
School.
Those are, the values for R are not really related, the 8.314.
They are. They're the same. They're the
One's
same.
dealing with pressure and the other one's dealing with vacuum.
They're both the same
One has-
constant.
One has, like the 8.31 is joules per mole, right? But this one has liter ATM. So this is dealing like with a gas.
Right.
Yeah.
All right, what's a good one next? Does anybody have any that they struggled with on the review in particular? Have you guys have done any? Yeah.
I haven't studied.
Huh? I'm assuming you've all done it, yes. I'm assuming you've all completed. Yeah.
Bigger assumption.
Bad assumption, okay.
These 2 Fridays I've already studied.
That's my excuse.
Yeah, let's do this one, yeah? So notice we have gases, right? Gases produced.
We're gonna be using accidentally.
No. This is great. This is a great question. So, I'm gonna go down until I get a bunch of space. All right. Dang, I can't really read the question, huh? Yeah. How's that? Can you guys read that? Okay. So we have gases, right? Right off the bat, Kp is equal to Kc, right? Right off the bat. Okay, but they're not asking that yet, right? We don't care about that, right? But you should be thinking that. Oh, Kp is equal to Kc. Cool.
Because they're all gases.
Because they're all gases, and they all have the same moles on both sides, right? 2 and 2, yeah. Kp is equal to Kc. We have 2 moles of hydrogen and iodine, and they're mixed in a liter flask. So if I'm solving for molarity, my moles are equal to my molarity.
Right.
Because I'm dividing by 1.
Right.
That makes sense, right? So that makes your life easy. And we get 3.5 moles of HI at equilibrium. So what does that mean? So that means that if I have an ice table, right?
Then 2.
What's my initial amount of both of these?
2.
2, right? So it'd be 2.0. I probably write the reaction, right? So it's
Right.
2 HI.
Right.
Yeah, I don't want. It was a little off center, so I don't want. All right, 2.
Right.
How much? What's my initial reaction? Or my initial amount of this?
3.5.
No, right? Because I'm not in equilibrium, right? Yeah. So it would be
At
0.
equilibrium.
So yeah, take a moment, right? Dissect the question. At equilibrium, you have 3.5. Cool. All right. So then we have 0 here.
I'll look at that. Yeah.
Do I know any information about these?
Yes.
Of these at equilibrium?
Oh, no, none of those 2.
No, I don't, right? But I do know about this, which is what?
So then the change is.
What was the change?
Plus 3.5.
Plus 3.5, yeah. Using the molar ratio, what's the change in this? What's that divided by 2? With minus, that's good. Yeah, so it's minus. And what's the change? Anybody do 1.75? Yeah.
Are you sure?
I think that's right. That's yeah. That looks right.
That's right.
Does anybody understand and not understand why we have that instead of, like 7 or something like that? We could divide by 2 because of the molar ratio, right? I'm looking at you. Negative 1 point. Is that fine? So what's my net change here? 0.25. I've left equilibrium. That would have the same amount here.
That's it?
Not yet, right? Calculate the Kc at equilibrium. This looks super easy when someone's doing it for you, right? Because what do you do when you get the test? You guys look at it, oh, I know how to do this. Nate did it, was easy. I plug in 3.5 here, clearly, right? And you get it wrong, right?
Yeah.
Horribly wrong. You don't know what to do. So we're solving for Kc, so we got to set up our Kc equation. So Kc in this case is equal to what? Products over reactants, right? Hi squared, squaring it because of the coefficient.
Right.
H2. And I2. Great. Normally, if this wasn't 1 liter, this would be the step, or earlier, we would have divided by the total volume. Does that make sense?
Yeah.
Because when we're doing ice tables, we're using molarities. Because this is 1, we can kind of get away with murder here, right? We normally can't do this, right? If the volume was 0.5 of a liter, we would have had to have divided at the very beginning. Does that make sense? Yeah. So we're using molarities. We just plug it in. The 3.50 squared. I'm going to square this because there's 2 of them and they're identical. Is that fine?
Yeah.
You just calculate your answer and you're done. Cool? Done. That's our answer. Whatever that equals. What's that equal?
196.
What?
196.
96.
And then KP would be the same since it's.
Yeah, so if they actually asked you what's KP, you would be, oh, 1.96. Right? Easy money. Yes? Oh,
Okay, is everyone sure on this part?
because this is pivotal, yeah. Out of curiosity,
Do you have a question, John?
Um, Fenton brought this up, right? Would this change if I was going this direction instead? That sign right there.
Oh, yeah.
You'd be negative.
It'd be negative, right? So that's something that they also usually don't test you on as well. But Fenton came to me explicitly and told me to tell you guys that if we're going in the reverse direction, all of these flip signs. Does that make sense? Yeah.
So your question just say, if, since it has the equilibrium, it would say it's going to reverse?
Yeah, or it'll say, what's the Kc of the reverse reaction, right?
And actually, then the numbers will change as well.
Yeah, the numbers would change as well, yeah. But all I'm saying is, be mindful of what direction you're going, right? If you're going this direction, the signs of these change. And that's very subtle. And it's kind of hard to give you guys an example of it unless I see it. But if I see one, I'll point it out. But if you're going to the left, please be mindful of changing the signs of these, okay? Cool.
Question.
Yeah. Question, you said?
Yeah.
What's up?
If you had a 3 and just
Where?
on the HI,
So you're saying if this was 3?
yeah, if that was 3,
How does that change this? If that's a 3 in the coefficient. Is that what you're asking?
yeah,
You cube it, right? If this was a 17, you would 17. You raise that to the 17th power.
I mean for your.
And also, this would be
Yeah,
really
it's like-
just wonk up everything, right? Yeah. You'd have to divide that by 17 or something like that.
No, but as for the other equation for the KP, the change in moles.
Yeah.
Yeah,
number,
so-
so then you would do 3 minus 2.
Correct.
And you get 1.
Right.
Yes.
Would you ever get like a 1/3 like that or a 1/2?
Would you ever have non-whole number ratios? You don't, right?
Okay.
That's a rule of chemistry, right? Yeah. That the coefficients will be whole numbers. Yeah.
Yeah.
So don't worry about that.
Okay.
No biggie. Yeah. Cool. Do a hard one. Yeah.
So the answer is always absolute, right? The absolute answer of.
By.
Let's say if the product is 2 minus 3 of the reactants, you get -1.
That would be your delta N. Yep.
It would be positive, right?
What do you mean, products minus reactants would be negative? If you're saying if your reactants was bigger,
Right.
it would be negative. Yeah, products minus reactants. 2 minus 3, you would raise it to the -1 power, which in essence would bring it down. Yeah. Like if you have x to the -1 power, what is 1 over x? Yeah. Yeah. You punch it into your calculator though, it's fine.
The RT will be on the bottom.
This one's hard. Ooh. Okay. You do? Go ahead. Number 9.
I don't look at it.
I want to see if you can do it, man. Honestly, yeah. Let's see. Remember
This
this.
is an interactive workshop.
Let's see.
So, you know first that you have 183 grams of SO3. It's in a 1 liter flask and heated to this degrees in Kelvin. The SO3 decomposes to SO2 and O2. You know that here. At equilibrium, the total pressure in the container is 1.30 atm. So find the values of the Kp and the Kc for this reaction at this temperature. Alright.
So you gotta find your moles, those in PV and RT.
Right. B equals.
Molar ratios, gas loss.
Idea, right?
And I'll just divide by P, or by V, because I want to find the pressure, right?
Right. Your grams molar mass?
You're
Can you
trying
guys
to
see that?
Partial pressure.
Yeah, because we have to find the partial pressure of this first. So, right.
Was it molar mass of SO3? Sorry.
Alright, so but first we also need to find the moles of the SO3, right, so that we can use that. So we know that we have 0.831 grams. And how do we find this?
Molar mass?
Molar mass, right? So what's the molar mass of SO3? You know?
80.06.
You guys don't have that memorized
SO3?
Alright, grams cancel.
It's like 101.
And then I get my grams, or my moles of the SO3, right?
0.01. 038.
That's it. Moles. Moles. Sig figs. Nobody cares about sig figs anymore, by the way. Yeah.
So,
How do you know to start with the PV and RT? Like, what was your first?
The fact that they give you grams is usually pretty helpful because if you have moles, then you can figure out the moles of the other things that got produced as well. And using the molar ratio of a balanced equation.
And you given an ATM?
Typically, I mean, do you guys have any tools with grams? Not really, right?
No.
But you do have tools with moles,
Right.
which is why it would be a good idea to just kind of.
Oh, you're
dive in.
asking, you wanna know why we use P, how do we know to even look at P equals NRT?
Yeah, I was just thinking what your first
because you see that here we have grams. So that I know right off
And
the
we're
bat.
talking about gases. They're all gases. if
You know
notice.
that that's a reactant?
Yeah.
So right off the bat, you know you need to find that for an ice table, but you also know that if you have this here, this chemical formula, you can use the molar mass, right, and find the moles of it. And you need the moles in order to use an ice table, right?
Can I tell you how I thought about it?
Okay.
I saw that I have grams. Once I have grams, I need to work with moles. I was working with moles in just about every equation in chapter 14, right? So then I thought about, okay, well, I got to convert it to moles, but I'm actually given ATM. What have I actually used before that is with ATM as well to get moles is the PV&RT, the ideal gas law. That's what prompted me.
So now I'll solve for the pressure of the SO3. SO3 equals the moles. I have the moles here, right?
It's a mole fraction or what?
Times the R, which is
No.
still the same thing as 0.0821 times temperature. The temperature is already given to me in Kelvin, right? My units have to be in Kelvin to use this. And
Peter
then
doesn't like units.
and then over the
Doesn't like
volume.
it.
Over the volume, and then my volume is going liter. It's just confusing. I don't want to do it.
I know, it only helps in every way. I'm
Yeah, it's
joking.
0.9374.
Yeah, it would. The data is just.
Right. You guys see how I did that? Now I found the pressure. That's like my partial pressure. So, now I can use this in an ice table, right? Because I want to find Kp and Kc, and I have this equation here, so I can do that.
I never used ice yet with pressures.
It's the same principle.
What I'm saying? Instead of concentration, just pressure.
Yeah.
Data, you're putting a lot of effort.
I know.
into
Sorry.
this.
It's taking too long.
Don't worry, we have.
I appreciate it.
Still trying to understand it as a grant, so you're giving us time to
I
think.
mean, that's how I do it too.
You guys draw boxes? damn.
Yeah.
Yeah, they're extra.
Right, it's more organized, right?
It's extra. It's an extra 3 boxes.
Alright, so I know the initial for the SO3, right?
Mm.
So I can just plug that in for here. That's 0.9374.
Okay.
Does it make sense why it says initial?
Yeah,
Yeah.
it's on the reactant.
Yeah.
Oh,
Even
yeah.
though it's not
Well, why is
molarity,
it initial?
Isn't it always in molarity?
We have another expression, right? We can use the KP expression, correct?
Right.
What do we use for KP? What's their units usually?
Okay.
Partial pressures, right? Yeah.
Right.
Yeah.
Yeah.
So partial pressures are kind of like analogous with like molarities, right? Yeah, because they're with respect to the volume it's in. So yeah.
We'll have to use partial pressures after this in order to
Yeah.
find the total reactants and the products. And I'll show you guys in a second. But alright, so let's just fill in the ice table for a sec. So this is the same, right? Since it's a 2 to 2. And this is 1, so you just do divide by 2.
It's 0.
That was a zero.
Never mind.
You're all good.
They asked me no question.
Yeah.
I would have done that too later. It's okay.
If you want, you can finish it.
Alright, I'll just finish it.
So why is it zero?
Because, so a reaction taking place, right? 0 because no products have formed yet.
Yes.
Oh, okay.
It's saying, so the question, sorry, not the question, the problem is saying that it's placed in a flask and heated, right? And they decompose to form these two components. So it's placed in the flask initially, there's no products initially.
So now the change, I don't know what that is yet, so I'm just gonna use an arbitrary number. So I'll just use x as my variable, but I'm just gonna keep the coefficient here with it. Right? That's what I use here. So it's minus.
Mhm.
I got that.
And then here, I'll just use x, right?
With the
And-
coefficient? 2x?
Right, so
This one will be 2, right?
And then what's this one?
So 0.
Right,
Oh,
and then
one.
these are formed.
Right.
We know that.
You see how I did that? You can do 1/2 2, but this is easier to do it like this way.
Oh, okay.
Okay, so then what are our equilibrium concentrations?
X, right? 2x. And then what would this one be?
Minus 2x.
Yeah.
Yeah.
Okay, what's the next step? Okay, how?
We have partial pressures, right?
So you know that the total of this is, right? So P
Oh, yeah.
total, remember Dalton's law?
Right.
Equals
All add them all.
the partial pressure of 1 times plus the partial pressure of 2, and so on, right? So I know the P total, right? Which is 1.30 ATM. So you have 1.30 ATM, I guess. Equals what? These are all 3 my gases, right?
So then what is he gonna make that equal to?
Oh, add it?
All those are.
You just add it all together, right?
Right.
Yeah.
Alright, this is a really long question.
Yeah. So I guess the grams and the total pressure is the signal of using X.
So then what do I do next? What's my fifth step?
So,
Right. So first step, right, combine like terms.
Right.
Add 3x minus 2x here, right?
Right.
Then that gives me just x. So we got 0.9374 minus x
Yeah.
equals this, right?
Right.
0.300. What do I do next? Just subtract this, right?
Yeah.
Right.
Do you need the number?
Negative X.
Well, you still have
Divide
negative,
right? Divided by negative.
0.3626.
Oh, there's saying, why is
And
this
then divide by
negative?
one.
They're asking us.
Yeah, why is that minus x?
3x.
Because
Oh, yeah.
3x minus
Yeah, it's
No,
just
yeah.
plus x.
2x.
Plus X.
Plus x.
Well, these, yeah. Yeah, because these cancel, right?
Oh, yeah. Understand.
Go that way, yeah.
So, yeah.
Easy.
So what is this one?
So this is point.
0.3626.
Right? So now I have what x equals. What do I do next? What do I need to solve?
Plug it back in.
I can plug it back in, right? So for the first one, which is SO3, right? At point 9374 minus 2 times 0.3626.
And that gives us 0.2102.
0.01.
0.21.
0.21.
0.21.
0.
0.
2.
So then, okay. That's my partial pressure of the SO3 now, right?
Right.
Did you see how I did that? Where's the SO?
SO3.
Okay. Now I still need to solve for the other ones, right? If I want to find KP or KC. So then my other one's just 2 times that, which is
0.725.
Yeah, 0.7252.
and then
252.
and that is for my SO2, right? You guys see how I did that?
Does that make sense, everyone? Yeah.
And then the last one's just what? This, right? Since there's only
Yeah,
X.
because it's just x, so times 1.
So it wouldn't be picky as for us to go and fill in the rest of the ice chart, right?
I'd be really picky, yeah.
He will?
No, don't worry about it, yeah, you're good.
Okay.
Just, I'll explain a little more after this, yeah. Do you guys get why you're doing an ice table for this or no?
Yeah.
A what?
An ice table?
Yeah.
Why?
See the difference?
You're just kinda doing it, right, yeah?
Yeah.
Because you're trying to look for KP and KC.
Okay, so what does that tell you?
Yeah, but you don't have KP or KC, right?
Right.
You need to solve for your equilibrium concentration.
Right, so we use an ice table because we have an initial condition and we're trying to find what it is at equilibrium. So we can use K and KC and KP because those are equilibrium constants.
So if they tie your hands, right, you can't solve for KC directly, right? Because you don't know it, right? So you have to use whatever relationship you know, which in this case is Dalton's law. Dalton's law connects total pressure, right? So then you can solve for each equilibrium pressure and then plug that in to solve for KP. And then we can solve for KC after it.
So, quick question, so if you had to solve for a QC, would you need an ice table?
For QC, no.
So we have one no. What do we got? No?
No.
What do you think? For Q, do we need an ice table?
What do you think? Can't hear you. No?
No? What? No? No.
Because Q is not at equilibrium.
So it's not. That's exactly it. Q is not at equilibrium, and ice tables are only used for equilibrium.
Right. Q is at any point.
So now I can solve for KP, right? I give you KP, which is what?
KP equals KC? Oh,
Well,
right.
then we can also find it a different way.
Product over reactants,
Okay.
right?
Products of reactants.
To there.
Yes.
Okay, QP, we would have to put 0, 0 for the product? Technically, we wouldn't be able to, right?
Yeah, right, yeah, because your QQ would be weird.
So then what do I use for my products and my reactants?
Your SO2.
Right here, right?
Over
These guys?
E.
If you put those over each other, you get 4.2 for your KP. Yeah.
You wouldn't be able to solve for KC first.
Can we? We have pressures. What's the units for KC? Or what do we use to solve for KC?
Aren't you supposed to multiply by
Polarities.
X and you used,
Right. Polarities, right? Yeah. But we have gases.
Wait,
But we do have a way to solve KC when we have KP though, remember?
this part, you're using
That
this
equation,
number to
right?
multiply, aren't you supposed to use this number?
Remember, KC
Divided by
is
2?
equal to KP.
Oh, I see what you're saying, yeah,
minus
yeah.
KT. So, remember that?
Yeah.
Yeah, so they're gonna use that equation to solve for the other one. This one's like notably difficult, by the way, so.
What
It's
is
still the
that?
same answer, right?
Oh, she just asked
Yeah, it's
if
the same.
this, the
Same.
number that we multiplied by 2 was supposed to mean this.
I just
one.
put the wrong number there. I
Yeah.
put this on there in accident, but it's supposed to be this, right? Because
that's our X.
that's what X equals.
Uh-huh.
So at 2x, remember from here, trying to find SO2 comes.
Okay,
Partial
yeah.
pressure.
So these are my products, right? And then my reactant is just the SO3. So that guy's just on the bottom there. But then I also need to keep in mind my coefficients, right? So I usually just do that at the end. So for my my products, right? SO3 or O2 and then SO2 and O2. What are the coefficients for this? O2 is just 1 and SO2 is just 2. So SO2 is just squared, right?
Yep.
And then my reactant SO3, what's the coefficient? 2.
4.2.
I was like, oh wait, the wrong one's good.
Oh, okay.
Cool. So now we can solve for KC, right? Now that we know KP.
Right.
Using which equation?
The KP equals KC, RT to the change of. So that's kind of nice, right? It kind of reminds me of like the rate laws, right? So if you have one thing, you can solve for. Yeah.
No, this is RT.
It's RT, yeah, but you're gonna take the reciprocal test, because you're solving for KC. It's gonna be in the denominator of the RT, right?
Alright, so KP equals 4.2, right?
Ooh, we should.
Just rewrite it.
Huh?
No, it's, isn't it? Yeah, it's,
It's 1 over, right?
we're solving for KC.
But
We
first
have
just put in
KP.
the values, I
We
guess.
have KP, yeah.
So you're rearranging the equation?
Yeah,
Is that what you're-
you just solve for the one you want. Yeah.
So then my KC equals KP, which is 4.2.
It's KP
Oh, no, no, no.
RT delta N.
Yeah, so this guy goes P and C, solve for KC, yeah. There it is, yeah. I always miss those up too, yeah.
Yeah,
So
that's
now
right.
solve for
Yep.
KC.
You just have to rearrange.
Oh.
So divide by RT over delta N. Yeah.
Now you keep it the original and then
Now
make
you're,
a new
now you're fine, and
equation.
just make that, and then make that P.
No, make
Yeah.
your new equation.
Yeah, I think they'd probably wanna see it.
Yeah.
So-
Keep the original one and make the new equation. That's
It's
it.
what, KP? We're solving for KP.
Right.
Equals KC.
Right.
RT delta N.
Right.
I'm just gonna do algebra. So then my KC.
Where's the RC? I'm thinking of resistance and current, dude.
RC?
Too much physics.
RC current.
You guys remember the R?
Too much physics. Yeah. Dude, clearly resistance. And then big resistance and charge.
Point zero
capacitance.
eight to one.
Times T, which is, or, is it
RT. So, thanks to the physics.
so what's T here?
Yeah, so let's go over the physics behind this.
It's talking about violence, talking about physics.
And then what's the delta N?
Because that's really what's more
One.
important. It's the central science.
-1. So then it goes to the top. Yep.
And then what is this?
Your overall answer is 0.047. Dope.
I don't think he'll give us this, but. I mean,
Yeah, I don't.
It's just-
Very involved.
It's just cool to know. I mean, there's gonna be ones where we're gonna have to use variables for sure. Like to do X, he's definitely gonna give us those.
Just not maybe look for the partial.
Well, no, just know how to do this.
Yeah, I don't know how likely that is. That
It might be on your
Question.
TV.
Quick
Yeah.
question.
Yeah.
How do you get the, if it's to the -1 power, wouldn't it go to the top?
It does, yeah. If you punch it into your calculator, it'll bring it up.
It gave me,
Yeah.
it gave me 379.
Yeah, yeah, I think Troy was asking.
Mate?
What's up?
It gave me 379.
Yeah.
Thanks for up here, then it gets bad.
It should be to the 1 power, that's why.
Isn't that -1?
It's 1, it's 3 minus 1. 3 minus 2.
So we started off with P.
3 minus
over
2.
RT, right? So
Oh,
you
yeah.
rearrange that equation to
Then you go P.
just P,
Yeah.
so you can
I
find
think you'll
partial
feel this
pressure
one.
SO.
Hopefully not, no.
No,
So-
well, at equilibrium, that's what it
Should be 1.
Reactants minus.
Products minus reactants.
What was the initial, what did we do
Yes.
again?
The initial was what we used to P equals nRT. And we solve for P, the pressure was our initial pressure.
SO3?
Yeah.
Okay. Yeah.
So the general idea is if you don't, normally you would have a KP or a KC to use, right? You
Right.
don't in this case. So if you ever have gases, you use Dalton's law. Keep that in the back of your head, right? Dalton's law is going to be your ace in the hole for most of these, yeah. So I don't think I had this. I can't remember, honestly. Yeah. Hopefully.
It's just good to practice.
Yeah, you kind of like are opening your mind up for different ones, I guess. Open your mind. Number 11. Number 11.
Yeah.
Let's go down to number 11. Yes, but we haven't done one yet. We haven't done a standard yet. Yeah. This one's really basic, but we haven't gone over a basic ice table yet. So let's go over a basic ice table. So your equilibrium constant, that is your Kc, is found to be this guy right here, right? This number, if your initial concentration of NO is 0.5 molar, what are the equilibrium concentrations of each substance? Basic ice table, but we haven't done one yet. We're going to have to use the quadratic formula at the end of this. Cool? But because we haven't showed you, we're going to show you how. So ICE. So we have, they're nice to us. They gave us the molarity to begin with, right?
Okay.
If they gave us moles, what would we have to do? Yeah.
Divide
Divide by the volume, total volume, yeah.
Okay, so what is this, our initial or what, right? It says it in the problem.
Says it initial, right? So you have to break down these questions, right? This one's kind of nice actually. 0.500 molar of this one. I'm going to use this as my reaction. What's my initial of both? Zero of each. They don't tell us anything about it, so we're going to assume they're 0.
Because they haven't formed yet.
Yeah, they haven't told you anything. They're starting with it. Our change, we don't know, right? They don't tell us, but we do know that it'll be some minus, right? Using the coefficient. We're going to do what? Minus 2 times some factor x, right? We don't know the factor by which it's changed, but we do know it will be double that of this one, right? And this one's gaining, so we get a plus x, right? Our coefficient here would be a 1, and a 1 here, so it should be plus x and plus x. That's fine.
How do you know it's doubling?
Right
2.
here. Because of this coefficient.
2. If that guy was a 5, you would put minus 5x. That's it. Yeah, whatever it is. So we just add them all up. 0.5 minus 2x. I'm going to kind of omit sig figs at this point. I'm going to let you guys deal with that one. Okay. So we have that. What's our Kc expression? Our Kc is products over reactants, right? So we're going to set it our Kc equal to, the way I like to do it is normally,
Okay. So
I'll show you the way I normally like to do it because you save yourself a lot of extra work, right? So what I like to do is I write it like this, so N2, keep yourself oriented as well. Write what should go there. Yeah, let's see that.
2.
O2. 2, no, there's no 2 there. But that's 2, that's going to be squared. Yeah. Oh yeah, you're good, yeah. So this is our skeleton structure, right? Don't forget the coefficient of 2 there. We do know the value of that. Now let's just plug in our values we see here. Cool? So our Kc, it's a big number, I'm not going to write it. Products over the reactants, that would be x, and that would be x, right? In the top. So I'm going to write that as x. You could write that as x squared if you want to save some time. Cool? For the meantime, I wanted to write it, but I'm going to keep it as x squared on top. That's fine. Not going to go on the bottom there, but notice the coefficient of 2 here, so everything you write down here is going to be squared. So it's 0.5 minus 2x, quantity squared. Yes, because of the coefficient. This is a really nice trick. Notice that top and bottom are both to the second power, right? So we can rewrite this as the square up top here, right? We can rewrite this like this because they're both squared. We can get the square root of both sides and eliminate the square and all of the quadratic formula as well, which is good news, right? So eliminate it.
Do they both have to be squared on top to use the quadratic, or no?
Everything here on this side, if they have the same power on both top and bottom, you're in good luck, good news.
If it's not.
If not, what you would do is multiply this up to the top,
Yeah.
distribute, and then solve for x, which is a pain, but he's more than likely going to give you one in which you can get the square root of both sides. Cool? So we get the square root of both sides. So it's kind of ugly, but let's see. So that would be the square root of KC is equal to x 0.5 minus 2x. Cool? I'm going to multiply that up. I'm going to erase this side. Is that cool to erase here?
Yeah.
That's also not, oh, you got it. Thank you, Joaquin. That's very gentleman. Cool. So we get that. We get 0.5. I'll show you all the steps. Why not? Minus 2x. One never shows them the steps, right? Yeah. KC. Might as well. Great. You guys see that? All I do is bring that up. You can distribute the KC to both of them. Is that fine? So 0.5 times the square root of KC minus 2x times the square root of KC, thank you, equals x. Cool?
Yeah.
You're going to bring this guy, this is just a number, right? I'm not putting the number in because it's really large. So I'm going to add that over to the other side and bring the x over to the other side. So when I get that, I'm going to have minus x Is that fine? Can factor out the x. Factor out the x. Minus 1 minus 2 times the square root of KC, 0.5 square root of KC. This is the most algebra you're going to be doing in this class. It should be nice after this. Divide both sides by this and you solve for x. Not too bad, right? No. 2 times the square root of KC. Is that fine? Yeah, I'm going to erase this then.
Wait,
What's up?
so you factored out.
I factored out an x. Does everybody get that part, yeah? Anybody need a factoring review? Cool. So then this effectively cancels. We have x is equal to 0.5. I'm going to plug in my KC value now, which is that guy, the square root. See that? Minus 1 minus 2 times the square root of 2.4. That gives you my x. What does that equal?
0.247.
0.247. Molar. Cool. We kind of eliminate our ice table, but ideally you still have it in front of you, right? And our ice table was that would be the concentration of both of these, correct?
Yes.
Right? So I don't have it in front of me anymore, but so yeah, this was going to be this was a value x, and then this one was 0.55 minus 2x, 0.50, right? So all I'm going to do then, since these guys are equal to that, you already got most of your answer. Plug in that 0.50 minus 2 times 0.247. You get your answer for the concentration of the NO. Cool. So this is a straightforward ice table, but it does have variables, which is the issue, right? If they don't give you the change, you have to do the minus x plus x plus x. Cool? It's not horrible, but is that cool?
Why did you move the 0.5 to the other side? On the third, from the second to the third step?
This one? Oh, to isolate x?
Yeah,
Yeah, so this is just a number, right?
Yeah.
Some number times some other number, so I brought it over, and I brought all of the terms that contained x on one side.
or what you could have also done was add this one to this side and
Yeah.
divide that side by.
Yeah, either way you want to do it, yeah. What you want to do is isolate the x's on one side and then factor. Cool. Awesome, that's it for that one, yeah. You got 10 minutes. You guys want one to choose one, or? Yeah? So do you have any ones that you guys are really complicated with, that you guys don't like?
Sorry.
We'll do one more.
is a cool vacuum.
It's cool?
Yeah.
Ow.
No power to it.
Oh, I see what you're saying, okay.
Which one's better, 12 or 13?
12 or 13. This is going to be one where you're likely going to see. I mean, either way works. 12 or 13.
Not harder for trickier.
That's fine. If you said 12, 12.
They're both good. They're both really good.
There you go. Yes, sure.
We can do both,
We'll
we
do
go
both.
fast.
Yeah, we'll do 12. Yeah, we can do both. We go fast, I guess. Yeah. Yeah, but what we'll do is we can stay past to finish the 13 one. Yeah.
Can you say an example of what he could combine? You know, he likes to combine things. Like first you gotta do one part, and then you gotta do the other part, then you gotta know.
That one that you
them all
guys saw
together.
with the ones with the moles and stuff like that, with the partial pressure and Dalton's law.
Okay.
That's worst case scenario,
Oh,
right?
Or is there any in the book that you saw that you think?
Not really, honestly. This particular chapter is pretty tame. You're pretty good. Yeah, this one's not too bad. He's not going to give you guys some crazy cubic function, right? He's going to give you a quadratic like this, like. So yeah, we'll knock out this one, the next one, and we'll call it. So, all right. This reaction has an equilibrium constant of Kc equals that. If you have, I like this one. If you have 1 mole of that, it's placed into that. So when you see placed, you can think of that as initial.
Right.
Initial. Yeah. Cool. That's what you think. This is like keywords. Flask allowed to come to equilibrium. What are the equilibrium concentrations of each substance? So they don't tell us the explicit change of every reaction, right? They just tell us that, what would they be if they came to equilibrium? So we're gonna have to use variables. So we're gonna use, notice that this is 500 milliliters. It's not nice like before where we had 1 liter,
Okay.
right? So we're gonna have to divide by the total volume, right? We have 0.1 mole, right? So 0.1. Somebody please give me that answer if you can. That 2? That just straight 2?
Do we have to convert the milliliters to liters?
Is that milliliters? It is.
0.2
Yeah. So
divided by 0.5.
yeah, I kind of did that without thinking.
Gives you point
Yeah, I
five.
could have did that. Yeah. Sorry about that. Yeah. Did you guys catch that?
0.2.
This was 500 milliliters, so we had to make that 0.5
Right.
to make that liters. Right? We're gonna do that jump like that now to save time. What is that? You said 0.2? Molar. Yeah? Molar. We use an ice table. Make a smaller ice table this time. 0.2 molar. Do we have any starting amount of anything else?
No.
Well, this is actually going the other way. Ooh. Ooh, I like this.
Okay.
Nice. Right?
Right.
I didn't calculate anything else. I calculated this one. So this is going to be this. Did you guys see that?
Yeah.
Okay, that's what Fenton told me to do, so I'm glad. I'm doing my work. Okay, so do we have any amount of this? We don't, right?
0.
At 0.
Right.
Where is this reaction going to go?
To the left.
That way. So what's the sign of this?
Plus.
Negative.
Oh.
Negative, right? You want to do positive, we do negative, right? And what's the, is it negative x or is it just, it's negative 2x, right? That's the change. So it'd be plus x and plus x.
Okay.
Do you guys see why we did that? Yeah? Yes.
So in this case, since, you know how you said it originally is gonna say reverse, this one you just go based off the actual equation.
Because what they gave us, right? They didn't tell us going this way, right? So this is like using your knowledge, right? I'm going to give you some of this. Which way is it going to go? That way,
Electrolytic could go either
right?
way.
So it can go both ways, right? So yeah.
Is that why it's negative over there and positive over there?
Correct, yeah. Normally reactants are negative, right? But because I'm losing this one, it's going that way. Is that cool? Cool. So then we just got to do our math. Plus x, 0.2 minus 2x. Is that cool? In this context, what are my products and what are my reactants?
The products is BR.
These, right? So then if we're doing our K, our KC would be products over reactants. But we kind of have to break ourselves from the convention that this is always products, right? In this particular context, these are going to be on the top. Cool? So that means that I'm going to have x and x. Is that cool? I'm going to write that as x squared to save time. X squared. And in the bottom, it's going to be 0.2 minus 2x. And this would also be squared, correct? So we're going to have a pretty similar situation to before. Because everything on top and bottom is being squared, we can write that as a 2 up here. Cool? And we can get the square root of both sides. Well, this is going to be equal to our k, or kc value. So this is what? 6.90? Okay. So that's the square root of 6.90 is equal to x over 0.2 minus 2x. Is that fine? We're just going to solve for x. We can do all the multiplication for this. Do you guys want to see that, or
Yeah, can you do it?
we'll do it? Okay. So I'm gonna do it over here on here. So that would be.
It's 2.6 the square root. Can you use the number 2.6?
You want to use that? Okay. Yeah, that's nicer. Yeah. So she's saying that this value here is going to be 2.6. So instead of writing square root of it, we're going to replace it with 2.6. Forget about sig figs for the time being. So that's x equals 2.6 2x, right? I'm going to distribute the 2.6. What is that? 5.2? No, what is that? 0.52? 2.6 times 0.2. Somebody do that for me, yeah?
0.52.
Ah, nice. 0.52 minus, that would be negative 5.2, right? 2?
No.
Yeah.
2x. X.
I'm staying quiet. I gotta go and practice my multiplication.
We're going to factor out the x in this case. These guys both share a common x, so I'm going to factor it out. That becomes 1 plus 5.2. Sorry, actually I don't need to do that, right? Yeah, I can. No, I can just add them together. Even nicer.
Yeah.
Let's just do that. 6.2?
6.2.
That's nicer. If we divide both sides by that,
6.2.
what is that? That's 0.52 divided by 6.2. Is that cool? What does that equal?
0.0.
Come on, can you do it in your head, please? Quick. What does it say? Did it turn off? Yeah.
No, it didn't.
What is it?
2.6. Actually, no.
That doesn't sound right.
Hold on, let me, I got you, Nate.
0.084.
It's different from the answer here.
Probably.
0.08.
0.08?
Wait, sorry.
0.084.
Oh, yeah, 0.08.
0.086. They have 0.086. We rounded at some point. That's probably right. Yeah. So that's going to be our concentration of be this and that, right? So then if we want to solve for, that would be that one, and that would be that one.
Right.
If we want to solve for that guy, we're going to plug it into the equation. So we have 0.2 minus 2 times 0.084. What does that equal? Anybody have that? Also, when you get your answer and circle it, a pretty formal way to show that your answer is a concentration is to put it in brackets like that. So that's like a formal way to answer it. Yeah. So what does that equal? 0.032?
I gotta try it. Yeah, 0.032.
Is that fine?
Yeah, got it.
That's 0.2, yeah, that'd be 1.6 or something like that. Yeah, that sounds about right.
Yeah.
Cool. That doesn't matter. The specifics aren't really the big deal in this case, right?
Okay.
The way we did it though, I like this question because it's making us go this direction, right? So getting us used to going in the left direction and making sure our sign is correct.
Mm-hmm.
We don't care about the sign as long as we're accurate, right? And we're consistent, right? We're losing this and we're gaining this. Keep track of that. We'll do one more.
So you said just write it in the brackets?
Yeah, that'd be a good way to show your answer, yeah.
BR.
And then in molarity. What's up?
Can you just leave like that? Do you write the square to it? Sorry, I missed that last part.
What's the question?
What's up? Yeah, go.
Uh,
Yeah.
Did you say you said that's 0.032
Yeah, that's how you would write that, yeah. They flipped it, it's fine. That's weird. It should be the same though. Or, oh, you know what we'd have to do is have to write 1 over KC, sorry.
Up there? Or here?
Yeah, we'd have to do 1 over KC.
Mm.
That's one, yeah. Yeah, so that's a good subtlety, yeah. So, go back up, yeah? We missed one step, yeah.
Oh, unless it's reversed.
Yeah, so, go back up, yeah, is this it?
This is it.
Yeah, this guy right here, I even missed it myself. So if KC is equal to this number, this is for the reaction below,
Oh, shit.
which is this charade, right, yeah?
Right.
So that means that if I'm going this way and using that convention of minus and minus, the KC of the reverse would be 1 over KC.
So you could do it the regular way. Right?
You can do it that way, yeah, if you want to do it that way. And that would, all that means is that, it makes sense. That number is equal to the products of this over that. I kind of want you guys to try it the other way, but yeah. So you have to avoid that mistake that I made, yeah. So 1 over KC equals that. And that would equal the KC of the reverse.
You could just use that number instead of.
Yeah.
So we did all that work for nothing?
Yeah. Yeah, it'd be 1 over that, yeah. If you wanted to use it the same way. You can, everything can be the same, right? It's just, if you want to use that value, it's this over that.
Gotcha.
If you want to do it the reverse
Yeah,
way.
yeah, so it's 1 over KC, that's why. Yeah.
Fast reaction.
Yeah, even I can't even catch it sometimes, yeah.
Yeah, makes sense.
That makes sense, actually, yeah.
Thank you for catching that.
Thank you, yeah, that was a good catch, thank you.
Yeah.
Got one more.
So we just erase everything.
Just up to the K and then.
Just under the N, yeah.
Yeah.
Everything up to.
Anything you had K,
So then all you gotta
just
do,
change the number.
all you gotta do is put 1 over K to this.
Just one number.
It's 1 over KC, that's it, that's all.
So that'll be the
So you'd be 1 over
root of that.
6.10,
That's what I'm asking.
Yeah.
and then.
One over.
I'll do it.
So
If
if
you,
you-
if you print out the worked out one.
Oh, yeah, that's right. Is that how we figure it out?
Because initially he flipped it.
Yeah, I wanna show you guys that one, so the way, I'll show you the way it's supposed to be.
Because I want to see how his worked out compared to this one.
So we said it
Is
was.
next to you during the exam?
It's just the review sheet.
Oh, that's what you, they give it there? When did they ask you?
That's how we solved for the other one, right? Yeah?
Yeah.
Yeah, so we can't set it equal to the KC that they told us. It should be 1 over the KC value. Yeah, it's very subtle. Yeah, I didn't catch it, yeah. So it should be 1 over 6.90. So whatever that number is, you're gonna plug that into there.
But everything else is the same.
Everything else is the same. Yeah. The way we did it was fine. It's just that the KC value needs to change. And then everything would be fine after that. Cool.
Minus 7 points.
Minus like 5 points. I mean, yeah. No, he probably would have gave us like most of the credit there. Yeah. Because we were bold and we tried flipping it, right? We were bold. Yeah.
Two bowls.
Too bold.
Two bowls.
Yeah. All right, can you see that?
But he said it for a reason, right? So
What?
if you can solve it the same way, then why even mention it? That if it goes in the
No. So the reason why he told me
Is it
that.
just so you can watch the piece?
No. We did something different though. We said the sign was different. The minus 2x was on the product side. That changed. That mattered. Right? On the previous one, we had minus 2x on the product side. So that was different.
Right.
Yeah, we would have got it wrong completely if we didn't do that step.
Yes, sure.
Cool? Yeah. So that's the difference. Yeah. Just remember that K that they give you is for the forward reaction, not the back reaction. You want to get the back reaction, K, you have to do 1 over the K. Right. Do you want to go home? Yeah. Sure, is it good? I'm sorry, sure. Sorry. It's in 1 edition. All right.
Oh, the library's closed?
Yeah, they closed at 4. Yeah.
Oh, fuck.
Sorry, we'll get it. Okay, a mixture of H2, I2, and HI. Notice they don't give you anything, right? You have H2, HI, and
It gives you molarity.
You don't have the equation.
You you don't, right? But you do know that
Right.
you have to write one, right?
Yeah.
That's gonna form HI, right? What are we gonna do? The two in front, right?
Right.
We have to balance that. Is that fine?
Right.
That's the next step, yeah. Okay. You dip in two?
No, Joaquin's right here.
Oh, lucky. An equilibrium mixture of that contains, at 458 Celsius, we'll highlight the important stuff, contains 2.25 molar of that. H2 and that. Not 5 liter.
And the third one, so.
Yeah.
Yeah, this is.
So our total volume is 5 liters. Now we have molarities for each of these, right?
Yeah.
So we can use this equation. So, see you later, man. Yeah.
Oh, all of these are gases.
They're all gases, yeah.
Right.
Hey, was it? Never. Is this any shit over there?
Over here? No.
Just make sure you guys sign it.
Did everyone sign in? I didn't sign in. I'll be fine there, so.
Well, that's straightforward, yeah.
Fine there, so next.
So you take it from the side.
So do we have to take the molarities?
Yeah, we just have to plug it in. It seems. Nah,
Nah,
the hard part was this.
It's not like that.
Yeah. So then we just got to plug it in. Yeah.
So we add in
So there's ice
0.01.
They gave us
moles of
molarities already, right?
Yeah,
Let's
so.
plug it in, right?
Don't do anything with the 5
No,
liters.
no, we don't need it. Yeah.
We don't use it at all.
No, we don't need it. Yeah.
If it was
The
in
point
moles.
zero one moles?
It was in moles, yeah.
Cross it out. What are the equilibrium concentrations when equilibrium is reestablished? Okay, that's why. This is the reason.
Yeah, it's moving the.
Then you use it.
So he actually did bring this up to me too to show you guys. So
Oh.
good thing you're staying. Yeah. Okay, so what would be our initial here for H2? We'd have to find it here, right? What is that? 2.24.
Yeah.
I2, the next one, same thing, right?
Right. And then 0.155.
Cool.
Right.
Now we're gaining this, right? So what is it going to be? Minus x plus 2x. Cool. Solve for that, and we're going to solve for our Kc. So 2.24.
It's just 224 basically. No, that was 0.002.
0.002. One zero in front of it, yeah. Do a normal Kc value. Boom, boom, boom. That's it, right? Yeah. After addition of 1 mole. Oh, I see. Okay. 0.22.
So they didn't use that?
0.1 mole of HI. That's 175. That's why. Okay.
So we don't know the change to these X.
We do need to use it. We do
Yeah.
need to use that.
Because it's like the stress, isn't it?
So it's after an addition of 1 mole of HI.
Yeah.
Right.
Contains an equilibrium. Okay, so these are equilibrium. Okay. And then we add a mole of this. Yes. Okay. So what we have to do, we're changing the concentration of this one. So we have, what was our original? Because we're adding 0.1 mole. So we need to figure out our new mole amount of
Right.
HI. So what we do is, we have it down there, 0.155 molar. Can we add moles to molarity to get the new molarity?
No.
What do we have to do first?
Molarity?
Get it to moles, right?
Right.
So yeah, that's what we're gonna use that one for. Yeah.
Or you can convert
Yeah,
the
so-
0.1 molarity to, moles.
So we're gonna get solved for moles. So molarity times liters equals moles. Cool. So we have a 5.0 liter flask multiplied by the initial molarity of 1.155. Gives me my mole amount of that. What is that? Somebody do that math? 0.175?
Yeah. Why don't you just do?
You can go the other way, right?
5 liters?
We can also, then we have to add that.
You can go the other way, right?
What do you mean?
You can go the moles, convert that of HI into molarity. With the
Can you add
volume.
molarities?
But look at the, oh.
Can you add molarities? It's a good point.
Gotcha.
If I have a 15 molar solution, can I add that to a 3 molar
Yeah,
solution
no,
and
you
get 18
can't.
molar?
You can't. Yeah.
No, right? Yeah. You have to add the moles and then divide by the total volume.
That's true.
That's the point. So add that to our 1.1 mole. Divide by. Is that cool? What does that equal? 175. They just added that like that? That's weird. No, let me see. No. I think you. No. It's supposed to be. That doesn't make sense. You can't. Oh, because they're divided by the same liters. I see. Do you have any calculator? Yeah, because they're not showing the steps on this one. Okay, they're not showing it. Yeah. Let's see. Oh, geez, you have a fancy one.
I get the 0.175.
No, that's hitting.
Isn't it 775?
Yeah, that's fine.
Okay.
Yeah, because I asked Dieter what the one was, and he gave me the total with it already added.
Gotcha.
Yeah. So if you multiply 5 times 0.155, right, you get 0.775.
Right.
And then you add the 1 mole.
Yeah, he gave you the answer.
And you get 0.17. Yeah. That's
Okay.
yeah.
Dieter.
Dang it, Dieter. Yeah. So this answer was what?
0.175. Oh, that one is 0.77.
0.77. You add that, divide that, and then you get what's your new molarity? 0.175.
0.175.
Cool. So yeah, if you look at ProfPads, they don't show you those steps. They just say, there's the moles, the new molarity. Does that make sense?
That's the one that you use in the ice trap.
Yes. So we're going to plug that in here. We're going to change that. 175. Is that cool?
Yeah.
Yeah. 0.175. Now we just got to do a normal ice chart itself. Yeah. So the only thing that changed is that they said this was already at equilibrium. We're adding some stress to it. So we're going to have to add the moles, essentially. So we got moles over liter. We turned our molarity, which was initially 0.155, multiplied that by the total volume, and got our mole amount, which was 0.77. We added that to the addition, which was 0.1 mole, and we divided it by 5, which is our new volume, and we got 0.175. So this is the new value I have to plug into my ice table. That's just recapping what we did. And everything here is normal. Oh yeah. So then, because we added an addition here, what happens to my using Le Chatelier's principle? What's the direction?
To the left.
To the left, right? Which would mean what? This is what, plus or minus?
Minus.
Minus, right? And plus. And plus. Do you guys see that? So yeah, we didn't even catch that at first. We were just doing a normal ice table. This is the key is that this says is at equilibrium.
Right.
So if it's at equilibrium, you have to pull yourself back and say, if I add that 0.1 mole, it's causing a stress. Which way is it going to shift?
Right, to the left.
It's going to shift to the left to accommodate for this. It'll go this way. So now that explains our minus x, our plus x, and our plus x.
Right.
So that becomes minus. Minus. Plus x and plus x. And then we do an ice table. So this is applying Le Chatelier's principle to an ice table problem. The key is that they tell you it's at equilibrium. It's a hard problem. Yeah, it's good. This is the last one on
You have
the
to keep
sheet.
solving from there?
Yeah, you want me to keep solving?
No.
No? Do you guys, yes and no's, yeah? Notice that these guys are they're gonna be the same, yeah? Yeah, so I'm just gonna, when I write it, I'm gonna square it. So we're going which direction? Or we're gonna use the same KC value they gave us, right? They say, where is
They
it?
didn't give it to us.
Oh, we're solving for it, right?
Yeah, you're solving for Casey.
Cool, so then we're gonna solve for it, yeah. So what would that be? It would be going in which direction? We'll do products over reactants. Since we're going that way, we can call it that way, it's products, I guess. Which way do they wanna do it here?
The no, the HI is a product.
They call that the HI still?
Yeah.
That's weird. Cool.
I mean, are we just assuming that because,
Because that's the way the reaction is, yeah. Yeah, that would be the KC of the forward reaction, which you can do either way, yeah. You can do it the other way, but it's gonna, whatever value you get, you'll have 1 over that, yeah. And you could probably argue that the reaction is now this way. And I'm pretty sure you would get no points docked off that way either. You know what I'm saying?
because you're adding more of it?
Yeah, because in essence, your reaction is no longer going that way, it's going that way, so. So then it would be H2. And that would be.
Is this how they do it in the answer?
Yes. For some reason, he always consistently uses it this way.
Okay.
But either way works. Yep.
Okay.
Yeah.
But just flip it if you did it.
47.9.
Yeah, your answer would be the same, yeah. So if you plug in your values here, right? These guys are the same, because they have the same molarities. They're gonna be squared on the bottom. Do you guys see that?
Yeah.
So that'd be 0.175, yeah. Squared because of the power here. Times 10 to the minus 2 plus 7x, yeah? Is it plus 6?
Yes.
Squared equals KC. Then you would just get the square root of both sides, right?
What did you square?
Yeah. Oh, these are the same.
Oh, because, yeah, gotcha.
Yeah, so these are the same, to avoid extra work, right? So you can, yeah, you can get the square root of both sides, yeah.
So in all fairness, you can even write the equation the other way.
Yeah,
Since it's not giving us an equation, we can just play around with it.
yeah. It's weird, actually, yeah. Solve for this. And then they solve for x, yeah? Using what k value? So they have 47.9?
Yeah, from this.
Oh, I see.
You got, yeah.
I see.
Then you solve.
No, but they have a 40, so that's actually true too. Look, you saw for KC before. You see that?
Yeah.
Oof.
So now you need to find the KC.
Yeah, so this is the KC of this reaction will be this, the K will be the same. Because what's gonna happen?
Right.
When you apply a stress, it's gonna go back to the old KC, right? But you still need to find that KC.
Yeah.
So what you need to do is an ICE table with the original values. Yeah. We were starting the way right correctly, actually. We needed to solve for KC first.
And then what do we do with the difference of the?
So it's not too bad. All we gotta do,
Plug it back.
because these are equilibrium concentrations, all we gotta do is put it in the equation. So what we gotta do is our KC initial,
Okay,
it's just
that's not so bad.
products
That's
over
not so
reactants.
bad.
It's not so bad at all, yeah. It's just products over reactants. Cool? Our products in this case are HI, and our value here is here, 0.155. Squared. 5 squared, and they tell us our other ones. Those are equal, so you can just square the bottom. Yeah. So it's going to be 2.24, 10 to the negative 2 squared. And that would equal our KC, starting. So notice that that's actually really subtle as well.
Yeah.
Your KC will be the same because it's going to equalize. It's going to come back to normal. That's really
It
subtle.
doesn't depend on the constant.
It doesn't depend on that. Yeah, you're applying some stress, and the whole idea is that Le Chatelier's principle will return it back to normal. Yeah, that's really, really, really subtle. So what is that, 47.9? So KC equals 47.9. Cool. So that means I can plug in that 47.9 over here, and now I can solve for x.
But then your signs will still be the same, right?
Everything's the same.
Negative, the pluses.
Everything's the same, yeah. So you get the square root, so then you can solve for x that way. What's the square root of 47.9?
Not when you try.
Don't even try to work. What is it?
6.92.
I multiplied the top up.
Was it a part B to it or?
No. Would you want a part B after this? Yeah. You distribute that and solve for x. I think we've done that enough, so you guys can do that, yeah. Solving for x. Add like terms and so on and solve, yeah. The x value you get should be what, Peter?
0.0022.
Molar. And that'll be the concentration, but we have to add that to these right here. And we'll get our finals. Yeesh. That one's not fun at all. That's hard, yeah, that's seriously hard.
That's like the PVO goes on our team.
Yeah, I would say this is probably one of the hardest ones that you can get, yeah. But it requires like a deep knowledge of what Le Chatelier's principle is going to do, which apparently I don't have, yeah. Because I didn't see that, yeah.
put in the ice chart minus 2x
Le Chatelier's principle.
because of.
If you add some of this, what happens to the reaction, the direction of the reaction?
Right.
You're increasing the concentration of this, it's gonna shift this way. That's, yeah, so there's like an all-star problem right here, it's crazy.
That's.
It's got everything in it.
That's based on the second ice chart. You were-
Yes,
the first
this is
ice chart-
this is the ice chart for, like, you know,
Part two.
stress, yeah.
But the first one you would've wrote minus x
Yeah.
plus 2x.
Yeah, well, no, we didn't even need to do that, because they gave
Oh,
us
right, 'cause you did it.
equilibrium
Got it.
concentrations, yeah. So we could solve for, yeah, right away, yeah. Each.
Wait, so, okay, so.
But you could do that initially, but then
Right.
if you know that you have the stress, then you read that later on, then you say, okay, the
It's
reaction's
gonna
gonna go this way, now I need to refix my,
Ah.
my number, my, positive, my negatives, right?
Maybe see what your value would have been.